welcome back to this unit on thermodynamics. So, in today's lecture 4, we will talk about determination of del U and del H experimentally, and then we will talk about change in enthalpy in different processes or in reaction. In last lecture, we talked about enthalpy and heat capacity. Just to recollect quickly, enthalpy we mathematically define H as U plus PV, and as U is a extensive quantity, H is also extensive quantity, and U cannot be determined experimentally absolute value. So, H cannot be also determined, absolute value of H cannot be determined experimentally. Del H is a state function. We also have seen that del U is almost the value of del H is similar to del H for solid and liquid subnet. In this case, we are ignoring the volume change in a process for solid and liquid, but for gas, ideal gas, we have seen that del U is del U plus del N G R T, which is change in moles, number of moles of gas. This is for ideal gases. We also have seen for any process at constant volume, del U is Q V, and for any process at constant P is del H is Q P. And we also seen for any process for ideal gas of course, closed system is there, del U is given by C V del T. C V is the heat capacity as constant volume, and we for this course we are considering C V is independent of temperature, and del H is C P del T. This is for, again one more time, this is for ideal gas. C P is always greater than C V, mainly for ideal for gaseous substances. For solid and liquid, C P is very close to C V for solid and liquid, and for ideal gas, C P minus C V is N R. So, these are the things we learned from last class. So, I will continue to ask few questions and see whether your understanding about these terms are clear or not. So, again I will mention a process and you have to tell me the sign of Q W del U and del H. So, that is question 7, continuing from last class. So, in question 7, first is reversible adiabatic expansion of an ideal gas. So, you have to tell me what is the sign of Q W del H, and obviously adiabatic, which means Q is 0 expansion. You know expansion means W is negative. So, del E would be also, this is Q plus W. So, it would be also negative. Now, we know for ideal gas del U is Cv del T. If del U is negative, Cv cannot be negative, is always a positive number. As del U is negative, del 2 must be negative. Which means, if I write now del U is equal to del H we know del H is del U plus del PV. Instead of PV, we can write NR del T, ideal gas. Now, del T is negative, delta U is negative. So, del H has to be negative. You can get directly also, del H is Cp dt for ideal gas, because delta T is negative, del H also has to be negative. So, I will move to the next example, which is 2. It is a adiabatic expansion of an ideal gas into vacuum. Now, quickly, adiabatic Q is equal to 0, expansion into vacuum. So, W is 0, Q 0, W 0, then delta U 0, as delta U 0 ideal gas, delta T 0, as delta T 0 ideal gas, delta H 0. This was easy. 3 is reversible heating of an ideal gas at constant P. We are talking about heating. So, Q must be greater than 0, constant pressure. So, Q P is del H must be greater than 0, ideal gas, hence C P del T must be greater than 0, hence del T must be greater than 0. If del T greater than 0, del U is C V del T must be greater than 0. If del U if del T is greater than 0, V del V, which is given by NR, we are talking about constant pressure process. So, P is constant. For ideal gas, del V is given by NR P del T. As del T is greater than 0, del V is also greater than 0, and as del V is greater than 0, W is less than 0. So, in this series I will give the last example, reversible cooling of an ideal gas at constant V. Again, cooling means Q less than 0, constant V W is equal to 0, del U Q plus W less than 0, hence delta T less than 0. Once delta T is less than 0 means del H C P del T, which is also less than 0. So, I just gave you a few examples how you can basically it will clarify your understanding and the sign of the process, different processes. We will mainly discussed about ideal gas. Now, we will talk about experimental determination of or measurements of del U and del H, how it is done in the lab. Now, the instrument which is used to measure del U and del H in the lab is called calorimeter, and the process or the reaction is carried out, the process or the reaction is carried out in a vessel, in a reaction vessel or the process vessel, whatever you call, which is called calorimeter, which is basically the vessel is immersed in water bath, mainly water bath, it could be other liquid, but mainly water bath is used of known quantity and known specific heat, of course, if you use water, known heat capacity. In this case, heat capacity and the weight or mass of the calorimeter is also known, or the vessel is known as well as the mass. So, from the if post the process or post the reaction, if we can find the delta T, we can find out the from the value of delta T we can find out Q. So, first we will talk about del U, how to measure del U, and the calorimeter we use is the name called Bohm calorimeter. And I have taken the picture from your textbook, and if you look at this picture, this is a Bohm calorimeter. Here what happened, this is a steel vessel. So, volume is fixed, they are not expandable, and sample is kept within the vessel. The vessel is called Bohm, and in this case we are showing example of a combustion reaction, so burning of the sample in presence of oxygen. So, sample is kept within the Bohm and oxygen is passed and sample reaction happens. Now, this entire Bohm is kept in a surrounding water bath, which is again sealed by adiabatic wall. So, any change in temperature in the surrounding means in the bath here, water bath here can be measured by the thermometer, and there is a star is also used, which just to make the mixing or the temperature uniform. Remember, this is the entire system is kept in a adiabatic condition. So, no heat is allowed to go out and come in, and because in this process the volume is kept constant, and you know with the volume process, constant volume process, we can get the delta U if we know CV of the material. So, once the reaction is over, we can find out from this thermometer what is the del T, and if we know the heat capacity for the surrounding water plus the bomb, then we can find out del U value from CVdT. This is, we can apply this expression because we are doing this reaction at constant volume. If you want to calculate del H, del U, as you found out that it can be calculated from constant volume process. Generally del U are obtained when by measuring the heat exchange at constant pressure processes, and generally we keep a the pressure is kept at 1 atmospheric or atmospheric pressure, and the heat which get exchanged or it generates, we call that as a heat of the reaction or enthalpy of the heat change which is associated with this reaction, enthalpy of reaction, and generally we use this symbol del HR. Sometimes we can also write del HR also, some books also refer at del HR. For exothermic reaction, if the reaction is exothermic, heat comes out. So, Q, and if you are doing at constant pressure, so QP is less than 0, negative, hence del RH also negative value, and for endothermic QP is positive. So, del HR is 0. So, you can, that is why if you do reaction, chemical reaction constant pressure condition, then we can write for the exothermic reaction del H is negative, and for endothermic reaction del H is positive. And it is simple, you can get this measurements done in a lab using very simple calorimeter, where the reaction is done inside this vessel, reaction vessel, and this is kept in a container. In this case, it is a foam polystyrene cup, which is basically thermal insulator. So, it basically prevents heat to go out from the surroundings or come in from surroundings, and there is a thermometer which measure the temperature before and after. So, once the reaction is over, from the temperature before the reaction and temperature after the reaction, you can get del T value, and once you know the del T value and if you know the Cp of the calorimeter used here, then we can get the value from Cp del T. Okay. We can get this because we are doing it at atmospheric pressure in this constant pressure process, constant pressure process. So, I will give you a problem again from your book and solve this here. I will just write down the problem from your book. So, it is question 8 for this course, where 1 gram of graphite is burned in a bomb calorimeter in excess of oxygen at 298 K and 1 atmospheric pressure. as per the following equation. C graphite during the experiment the temperature goes from, so T1 was 298 K and T2 is 299 K, which means del T is 1 K, and heat capacity is given at is a constant pressure. So, heat capacity Cp is given as 20.7 kilojoule per Kelvin. So, what is the delta H value for this reaction? So, it is given here. What is supplied? Delta is supplied, Cp is supplied. So, we can get Q as Cp delta T .7 kilojoule per mole inverse into, you will convert into moles. So, 12 gram per mole and it is for 1 gram. So, we put 1 gram. Now, it is a burning reaction in presence of oxygen. You know, in burning of any substance in presence of oxygen will produce heat. So, Q must be a it is exothermic reaction. So, Q is lost from the system. So, the value of Q must be a negative quantity. So, we put, just to take care of the sign from a system point of view, we will put a negative number here, which will give us this value as 2.4 to 10 to the power 2 kilojoule per mole. Again, just to emphasize about the sign, because in this case system is losing some energy, as this is a exothermic reaction. Any burning is a exothermic reaction, as you know. Hence, this negative sign is appearing in this case. So, the magnitude would be this, but the absolute value would be with a negative sign. So, what I will do, I will put one more question in front of you, which is question 9 in this case. So, we talked about all these quantities in last 2-3 classes, and then just to revise or recap the lessons, you just tend to tell me these quantities whether they are intensive quantity or extensive quantity. They are intensive or extensive, and obviously, as I said, unit is a very important thing in solving physical chemistry problem. So, you must remember the units or the handle units very carefully. So, density is a intensive quantity or extensive quantity is a intensive quantity, intensive quantity, and the unit should be kg meter cube per meter cube. Internal energy is, as we said, is extensive quantity, extensive, it is energy. So, the unit should be joule. This is molar enthalpy. So, enthalpy per mole. So, it must be a intensive quantity, and its energy per mole. So, joules per mole. Cp is a heat capacity at constant pressure. Now, it is a capital letter, as you see, you can see it is a uppercase or capital letter. So, it is a heat capacity, not molar heat capacity or specific heat capacity. So, it depends on the size of the system. The higher is the mass, higher will be size of Cp. So, it must be a extensive quantity, and it is a energy heat per Kelvin. So, it per degree rise in temperature. So, joules per Kelvin. This is a smaller letter C, so it is a specific heat capacity at constant pressure, constant pressure. So, per gram, which means it is a intensive quantity. So, it will be joules per Kelvin per kg. CPM is a molar heat capacity at constant pressure. So, it should be intensive again. So, again J K inverse mole inverse. Pressure you know it is a intensive quantity, and SI unit is Pascal. Molar mass is again intensive. So, most of the molar quantities or specific per gram quantities are intensive quantities. So, it is kg per mole, and temperature is of course intensive quantity, and the SI unit is Kelvin. So, we just to recap, we did exercise to find out whether you know which is intensive quantity and extensive quantity, and as I said, the units, you must be very careful about the units. So, you solve numerical problem, if you write the units properly, you are bound to get the final answer right. Next, we will move to the enthalpy of change of a reaction or a process, and we also call this as reaction enthalpy, or on the sign we write del H R, or in some cases we write del H R, but in this case your book, it is textbook, it is written this. So, we will use this as a representation of reaction enthalpy. So, in generally a reaction, a chemical reaction can be written as a set of reactants to products. So, by doing the reactions or by transforming reactants to product, there should be change in enthalpy between the products and reactants. That enthalpy change is what we call the enthalpy of reaction or reaction enthalpy. So, we can write the reaction enthalpy as sum of enthalpy of products minus sum of enthalpy P's, capital letter P's of reactants. If we can write AI H products minus BI H reactants, where AI and BI are the stoichiometric coefficient of the products and reactants respectively in the careful in the balanced. So, you have to, when you are talking about the stoichiometric coefficient, that has to be in the balanced chemical equation. Unless if you do balancing, you will not be able to get the stoichiometric coefficient right. So, these are A I and B I, they are the stoichiometric coefficients for products and reactants in balanced chemical equation. So, just to take a specific case, for example, if we take this reaction CH4 gas plus 2O2 gas, CO2 gas, 2H2O liquid, then delta AH reaction or reaction enthalpy or reaction heat of reaction should be given by, as wrote in last page, products minus summation of BI H reactants, which will be given by products means H M CO2 G plus twice H M H2O liquid minus H M CH4 gas plus 2H2 HM O2 gas. Now, what is this HMs? This HM is molar enthalpy of carbon dioxide in gaseous state, molar enthalpy of water at liquid state. So, HM is called molar enthalpy of the corresponding reactants or products. So, for exothermic reaction, as we discussed earlier, exothermic reaction del AR H should be negative, and for endothermic reaction del H R should be positive. And this is very important to know the value of these quantities, because if you are doing a reaction in a plants or in the lab, unless you do not know what is the amount of heat comes out, it will be very difficult for you to control the reaction. So, it's the value for when you are doing a reaction, a chemical reaction in the lab or in a plant, especially in large scale, then you must have idea about what is the amount of del H in this reaction, so that you can accordingly design your machinery or equipment to handle that heat generation in this case, or heat basically managing the heat which is coming out. It is also important if you want to know the temperature dependence of equilibrium constant. So, it is very important. Now, as you can see that del H R depends on the conditions under which a reaction is carried out, is not it? Reaction is carried out. So, we must know we must need to know a specific condition or the standard condition by which we can compare. So, we must know, we must need to specify standard considered, so that we can compare between the reactions, and we, so in, see if the reactants and products in standard conditions, reactants to products, if all of them are in standard condition, same here standard condition, then the corresponding del H would be del H R, and we put a superscript, degree superscript or not, whatever you can call. So, this signifies a standard heat of reaction of enthalpy of reaction. Now, you have noticed that we are talking about reactants in standard conditions and product in standard conditions. So, obviously, we will ask what is a standard conditions. So, we must define the standard conditions, and at standard considers the molar enthalpy would be standard molar enthalpy. So, Hm, we wrote Hm in few minutes back, it is molar enthalpy. So, if in standard condition we can write this as standard molar enthalpy. So, obviously, your question should be what is standard conditions. So, we must define standard conditions. So, definition of standard conditions. So, we can write definition of standard conditions, and we will limit in this course. We will talk about mainly pure substance. We will not talk about pure substances. We will not talk about the mixtures or in solutions. So, in case of pure solid and liquid, so this is what I said, we will restrict our discussion on pure substances. It does not mean that we cannot describe standard conditions in solutions or in mixtures, but for this unit or this course we will describe or limit our discussions for pure substances. So, for pure solid and liquids, we define standard state as pressure equals to 1 bar and at a specified temperature of value T. This T is the temperature we are interested in. So, basically say we can want to say that standard state of liquid water. So, if we want to tell the standard state of water, it will be a state where water is at 1 bar pressure and we have to specify the temperature. So, if we want to write standard of water at 25 degree centigrade, then the standard state of water at 25 degree centigrade would be water at 1 bar pressure and at 25 degree centigrade, which means the standard state is not a fixed state. It depends on the temperature which you are interested in. Pressure is fixed. For each standard state, we are mentioning that pressure is 1 bar. Sometimes we call this as a standard pressure, but 1 bar, but this will change as we change our temperature. So, if we just talk about molar enthalpy, standard enthalpy, then we must mention a particular temperature. So, in this case it will be molar enthalpy. Say if we talk about say water, then molar enthalpy of water at 1 bar pressure and at temperature T. If you talk about 100 degree centigrade, then it will be 100 degree centigrade. If you talk about 25 degree centigrade, it will be 25 degree centigrade. For gas, we talked about pure solids and pure liquids. Then we will talk about pure gas. Now, pure gas standard state is again P is 1 bar at temperature is equal to T, and there is a third condition we are writing where the gas behaves as an ideal gas. Now, you know that at 1 bar pressure no real gas will behave ideally at 1 bar pressure and at temperature any temperature T. Hence, for a gas, for a pure gas, this is something which is imaginative or fictitious. So, for gas standard state is, so since no real gas will behave ideally at 1 bar pressure, standard state we can write that standard states of gases, pure gases are fictitious states, which is not a real state, because really we cannot get a condition where the gas behaves as ideal gas at 1 bar pressure. Now, this is important. If we do not write any temperature, sometimes your book it is also not mentioned. As I said, a standard state, all the standard state will have a temperature. We have to mention temperature for corresponds to standard case, both in case of gas as well as we talked about in liquid and solids. But in case it is not mentioned, then you can safely assume that it is 25 degree centigrade, but this is incorrect way of representation without mentioning a temperature in standard state. But in case there is no mention of temperature in standard state, then it is usually meant that temperature is 25 degrees Celsius. So, you can safely assume that it is a temperature 27. So, we can assume temperature 25 degrees Celsius if no temperature is given or mentioned. But as I said, this is not correct way to define standard state. Ideally, every time when somebody refers a standard state, it should mention about the temperature, but in case somebody do not mention, you can assume that it to be 25 degree centigrade. So, we can for any reaction for the following reaction, A plus B to C plus D, we can write the standard reaction enthalpy. Now, you have to mention a temperature at T would be given by C HM T C plus D HM T D minus A HM T A HM not T B. Now, this HM, for example, HMT, this if I just want to mention this quantity, this I can write separately. This is standard molar enthalpy of A at temperature is equal to T. So, when you are talking about this reaction enthalpy, we should mention T. As I said, if temperature is not mentioned, then you can probably assume that T is 25 degrees centigrade. We can write a expression. Now, we can also imagine that this all this number A, B, C, D, these are what? These are stoichiometric coefficients in balanced chemical equation, which means these are they are unitless. So, they have no dimension, unitless quantities, which means this term will have the same dimension of this molar enthalpies. They all have same dimension, same units, which means del H R 0 T will have same dimension or unit as H M, which is what? Energy per mole. So, joule per mole or say calorie per mole. So, this is important. The unit of reaction, standard reaction enthalpy, that would be joule per mole or calorie per mole. Now, this is exception where we are writing per mole, but you will soon find out that this is not a intensive quantity, it is actually a extensive quantity. I will just give you example. Now, delta standard reaction enthalpy will depend on or depends on how you writing the expression, how the reaction is written, and it is a extensive quantity, even though its unit is joule per mole quantity. For example, I write expression equation this. This is a obviously first thing you have to check whether this is a balanced equation or not. So, once you check it is balanced equation and the delta H value, the heat change or heat of reaction of this reaction at 298 K is given by minus 572 kilojoule per mole. Now, if we consider all these hydrogen, oxygen and water in standard condition in this reaction, which is at 1 bar and this particular temperature, then we can write this is standard enthalpy of reaction this. Now, if I write the same reaction, I can write this way as well. This is also balanced equation. Here 2 moles of hydrogen and 1 mole of oxygen is reacting. We can say half mole of oxygen and 1 mole of H2O is reacting. In this case, the reaction enthalpy at the same temperature would be half of what we had earlier. So, depending upon how we are expressing the how the reaction is written, depending upon how the reaction is written. So, if the reaction is written like this, we have reaction enthalpy, standard reaction enthalpy of some number. If we write in different way, then it will be a different number, though we both cases we have per mole. If we write 4 to 4, then the number would be double. So, basically it is standard enthalpy change per mole of the reaction as we have written. So, I hope this has this has clarified that even though it is per mole term is written, it is not intensive quantity, it is indeed extensive quantity. So, if you double the amount, each of these reactions amount, it will be double. If you make half, then it will be half as well. Now, when we are writing this expression for reaction enthalpy at particular temperature, we are all referring to this molar standard molar enthalpy or molar enthalpy at standard state, whatever you call. Now, as you have seen earlier that the absolute value of H or absolute value of U cannot be determined experimentally, which means the absolute value of HA0M also cannot be determined experimentally, only it can be determined relative to something. So, we have to get this value relative to in comparison to something or in an indirect way, and for that we will define something which is called standard heat of formation. Later on we can show that instead of standard molar enthalpy, we can replace this with standard heat of formation. We will show that in the next lecture. Now, standard heat of formation is or standard heat of standard enthalpy of formation is we write again, this has to be a particular temperature. We can write this is for a pure substance at a specified temperature T is equal to the delta H 0 or reaction enthalpy of a reaction, or for the process or for the reaction in which 1 mole, remember we are talking about 1 mole here, of substance in its standard state at T is formed from the corresponding separated elements at T, each being in its reference state, or sometimes called reference form, or sometimes called reference phase. So, it is a quite long definition. So, delta H formation of a pure substance is at a specified temperature. We always have this temperature at which is equals to the reaction enthalpy for the process of the reaction, when the substance 1 mole of substance is formed from the elements in their reference state or reference form or reference phase, how do you call. Now, what is this reference phase or reference state of the elements, of the constituting elements, is the reference state or phase or form is the most stable state of the element at 1 bar pressure and at the specified temperature T. Now, if temperature is not mentioned, sometimes like in your textbook, it is assumed that T is 25 degrees centigrade. So, sometimes unless it is mentioned, sometimes if the reaction enthalpy for the formation reaction is not the temperature is not mentioned, then you can consider the temperature is at is equals to 25 degree centigrade. So, the you can reference state would be the most stable state at 1 bar pressure and at 25 degree centigrade. So, what I will do, I will stop now in this lecture, and then in next class on I will talk about the enthalpy change associated with other processes like phase change and in chemical reactions, and we will also continue our discussion about this reaction enthalpy little more or basically the enthalpy of formation little more with some examples.